Yeah.
Just chop.
See, the sooner I get started, the sooner we get out of here. You know, the sooner we can go for beers. I think we're actually recording, so maybe I should stop saying everything that comes to the top of my head. So here we are, last session of NDC Melbourne. Aww. Over for another year. Actually, this is my first NDC Melbourne. I'm acting like, I'm here every year. It's first time. As you see from the slide, I've met a few of you actually the last couple of days. Oh, wait, can we get the slides up on the screen? I got too fast for my slides. My name is Jodie Burchell. I'm currently working at JetBrains, as you can see by the big branding on me today. And I'm in developer advocacy at the moment. I come from a career in data science. So I've been a data scientist for around 9 years. And if you've ever done a data science project, this question, can I trust my model, might feel familiar. It's a question I've had to ask myself many, many times over the course of my career. And since the advent of large language models, this question has actually become much more tricky to answer. But of course, we're talking about data science. We are talking about a scientific approach to things. So trust is not really enough. Instead, we have a different question on our hand. We have a question about whether we're actually assessing the right thing. And what I'm going to show you over the course of this talk is how complicated this question can be and how interesting it is. Please, please, don't walk out just because we're talking about measurement. This is really cool stuff, very interesting. I'm going to show you some really wacky things. It's not going to be boring, dry math. But to kick us off, let's have a look at a story from around, lucky clicker is starting to die, from around 15 years ago, which helps kind of set the point home about the difference between trust and correct measurement. So in 2010, a social psychologist called Amy Cuddy was teaching at Harvard Business School. And she started noticing a difference in the behavior of her students. So she had one group of students. They were doing very well at their written assessment, but they were also marked on class participation, and they were not doing very well. The students were very shy when they had to do class participation. They'd half hold up their hands almost as though they were protecting themselves. And correspondingly, they got very low marks in this part of their assessment. Then there was another group of students. These students were doing very well at written assessment. This is Harvard after all. They were also doing very well in their class participation. So they would throw their hands up, and they would answer with a lot of gusto and a lot of confidence. And of course, they did very well. So Cuddy began hypothesizing about her students' behavior. This is the danger of studying psychology. You get experimented on by your lecturers. And she began to wonder whether this relationship between body language and confidence went both ways. So obviously, the conclusion you can draw is people who are less confident will show less confident body language. But she began to wonder, can you induce more confidence in people by getting them to hold more confident poses? And this kicked off Cuddy's research into what she called power posing. This, I see some looks of recognition. Yes, this story's going where you think it is if you know the whole story. So what she did is she got a group of participants and she got them to hold expansive, she called high power poses, like this one, the Wonder Woman pose. And she found that participants in this group showed higher levels of confidence. They reported feeling more powerful. They were more likely to want to engage in risk-taking behavior. And most importantly, they showed physiological differences. They showed lower levels of cortisol and higher levels of testosterone. So they basically were physiologically less stressed and feeling more dominant. So people went nuts when Cuddy published these findings. They actually got accepted into the top journal in psychology. And of course, Harvard did a press circuit. So Cuddy got interviews with the press. She appeared on Oprah, true mark of success in 2010, and she got one of the top TED Talks of all time. So people everywhere were sneaking into bathroom stalls and power posing before things like job interviews, or holding poses like that before doing something like, walking on stage and doing a presentation. So Cuddy and her power posing were a phenomenon. That was until 2014. A cornerstone of science is reproducibility. Another researcher, Ava Rainhill, tried to replicate Cuddy's findings. She found she actually couldn't replicate most of what Cuddy had found, in particular those all-important physiological findings. So other researchers started paying attention to what Rainhill had published, and they also contributed to this, finding this body of evidence that Cuddy's findings weren't actually valid. And this whole unhappy saga came to its head when one of the original co-authors on Cuddy's study publicly disavowed her findings, and Cuddy's credentials as a scientist were called into question. So what happened here? Was Cuddy a charlatan? You know, she ended up actually making quite a lot of money out of her speaking to her. She went on to write a book. Or was she perhaps incompetent? Well, neither of these things were true. Cuddy was a rigorously trained scientist. She did her PhD at Princeton, and remember, she was doing this research at Harvard. What happened was Cuddy was fooled by results that looked legitimate, but they told her the wrong thing because she had measured incorrectly. Now, I know what some of you are thinking because my PhD was in psychology. You are thinking, psychology, it's so unscientific. You know, of course this happened. But this can never happen in machine learning. It's so much more objective. We use all this super cool math. It's so advanced. Well, obviously I'm going to tell you, not so fast. That was a trap. A review was done after Cuddy's kind of saga happened. This is called the replication crisis in science. Reviews were done to try and see whether studies could be replicated across a whole range of fields. And what they found is that in many, many fields, at least half of the papers that were published that used machine learning methods at their core could not be replicated. They had results that were incorrect because they had measured things incorrectly. And I don't know what the hell is going on in satellite imaging, but 100% of the studies reviewed had such issues. And as you can see, this includes supposedly more objective fields like medicine, genomics, and oh no, software engineering. There we are at the bottom. So this leads us to a very natural question. How can we know if a machine learning model is good? If all of these so-called experts in machine learning, people who are adding to the publication record in this field, are making these mistakes, how can we know if we've measured the right thing? Well, we can see an example of how these mistakes can be made. So one of these studies was trying to pit different machine learning algorithms against each other. So what they did is they got these algorithms to solve the same problem on the same data. And what they found is that newer, more sophisticated algorithms outperformed a much older and more basic type of algorithm called logistic regression. And it seems logical, right? You would expect that something that is older and more basic is going to do poorer than something that is more complex and sophisticated. Except none of it was true. The authors had made major mistakes with how they had assessed their findings. And when these were corrected for, all of the algorithms basically performed the same. So let's think about how we can know if our results are correct, how we can not fall into traps like this. And we can borrow from a field of mathematics called measurement theory. Promise, there's no boring math, just cute pictures. So measurement theory tells us that a robust machine learning model has two different properties. One is reliability and one is validity. So reliability is basically knowing that the results you get are consistent, and this has a few different dimensions. The first is that for equivalent inputs, you will get an equivalent output. I put in the same data, I will get the same prediction, the same result. This will be stable over time. The model will give me the same result for the same data 6 months after I trained it, a year after I trained it. It will not drift if the data stays consistent. And different ways of assessing the same thing, say human assessment versus a machine learning model, will converge on the same result. Now, validity is something that seems on its surface a little more basic. It's basically saying that you have measured what you think you've measured. And it seems like, how could you get this wrong, right? But you will be surprised. You are going to see a lot of examples of how you can get this wrong and how people are getting this wrong with measuring LLMs. So again, there's a few different dimensions of this. The first is that you have a well-defined, concrete idea of what you're trying to assess. The other is that if you're trying to measure two similar things, they should have correlated performance on the same model. And finally, your model should perform just as well in its nice, safe sandbox, its development environment, as it does in the real world. So to have a look at some problems with reliability, let's have a look at one of the most serious issues you can have with reliability, which is data leakage. So in order to explain data leakage, I think the most easy kind of way to think about it is imagine that you are a professor and you want to give your students an exam at the end of the year. So what you can do is you can give them a bunch of past exams to train on, to practice with. But when it comes to actually giving them an exam, you will create a set of fresh questions. This way you're sure that what you're assessing is how well they've learned the material. But let's say, I don't know, you're a little bit lazy, maybe you're running low on time, and you decide to recycle some of those past exam questions. Now you've confused what you're measuring. Maybe you're assessing how well they have learned the course material. Maybe you're just assessing how well they've memorized answers they've seen before. So the exact same thing happens with machine learning models. And we can see this with the case of a model called ChexNet. So ChexNet was designed to assess whether people have pneumonia based on their lung scans. When it was first developed, it performed super well. Like, great, hooray for science, right? We have this super cool model. But of course, there was a problem. The issue is that people don't go in and get one lung scan at a time. They get multiple identical scans. And the creators of the model didn't realize this. So what they did is they divided these identical lung scans between the training set and the set they used for measurement. This meant that the model was essentially able to cheat because it knew some of the answers in advance. This is what data leakage is. So let's move on to our other pillar of machine learning model goodness, which is validity. So when we were creating the early models in machine learning, things like regression models and decision trees, it was super easy to measure validity because these models are completely explainable. You know exactly how they've made the decisions they've made to get to the predictions that they give you. And we can see a case of that with linear regression. So let's say we create a linear regression model in order to predict students' exam scores. What we have is a bunch of things that will predict those exam scores, features. And for each of these features, we have weights, beta coefficients. What these weights tell us is exactly what the model has learned about how that feature affects the outcome. So for example, if we have this coefficient of 1.5 next to hours spent studying, what it tells us is that the model has learned that for every hour a student spends studying, they will get an extra 1.5% in their exam. Very easy with linear regression and other such models. But as models have become more advanced, they've also become a lot less transparent, and we've entered what we call the age of black box models. So you can see this with a case of, say, vision models. This is a convolutional neural network. This is a common type of vision deep learning network. And what we can do is we can pull out the hidden states of these models, and we can see that it seems to sequentially be building up images of cats, learning bit by bit what a cat looks like. We can also see this with early, smaller large language models. Small language models, I don't really know what you'd call them, but the very early LLMs. So we can see that they seem to be learning the relationship between words in a sentence in order to make their predictions. But this sort of interpretation is somewhat piecemeal, and it's nowhere near as clear or as obvious as how you interpret linear and logistic regression models, decision trees, these smaller and simpler models. And things have really gone off the rails when it comes to LLMs. Now we have serious problems assessing their validity. We can no longer peek inside models at all. So the main ways we really have, actually that's not true. Model explainability has moved on a lot this year, and we have some ways of seeing how the models come to the conclusions they come to, but but it's not really holistic. It's kind of looking at only parts of how the models make predictions. Anthropic has a very interesting paper about this if you're interested in that, but let's get back to the main core of the talk. The main way we really are assessing these models is looking at the inputs that we give them and assessing whether the outputs make sense. So you can see in the case of this cat joke, it makes sense, but we don't really know how a model knows what a concept of a joke is and how it can relate that to the concept of a cat. And one of the problems that we now really have is that these models don't have reliability. So in the past, we designed models so that the outputs were deterministic, the predictions. The training methods may not have been, but once we had a model, if we put the same input in, it would give us the same output. The problem with large language models is when we first created them, if they gave us deterministic outputs, the speech didn't sound very natural. It didn't sound very human. So we built in a mechanism called temperature, which basically it's not quite random, but it does a sampling of the possible next words that can come and adds a degree of randomness to that. And that's increased how natural the outputs sound, and that's kind of necessary in order to use these models productively. But the problem is it's led to a situation where the outputs are not reliable. So I can put in the one input, write a joke about cats twice. It will give me two different outputs. The outputs are equally terrible, but that's more a matter of taste and not really a matter of measurement. So we come back to the question we asked about machine learning models. How can we know if LLMs are good? How can we know if we're measuring the right thing when we're trying to assess their outputs? So if you've been a person existing in the world for the past 2 years or so, you would have seen LLM providers telling you how good their models are. So you might have seen in the marketing material for the latest model that came out, something like the following. We just launched our newest large language model, trained with state-of-the-art GPUs, and we've improved on the MMLU by endpoints, beating the previous best. Or if you're more into the weeds, you might have seen some sort of variation of an LLM leaderboard, assessing LLMs on exotic-sounding measures like Winogrand and Hellaswag. But what does this all mean? Does scoring well on any of these assessments mean an LLM is good? What are they measuring anyway? And can I trust these leaderboards? Can I trust these statements of goodness? What we're going to be exploring for the rest of this talk is the wild, noisy, and confusing world of LLM assessment. So let's start with what I think is one of the perhaps most controversial ways of assessing LLMs, and that's using benchmarks that were designed to assess humans and applying them to LLMs. If you came to my talk yesterday, you would have seen me touch on this point a little bit, but let's get into it in a bit more detail. So when these models first came out, when they first started getting really sophisticated, particularly at the beginning of 2023, we started seeing results everywhere that these models were being applied to the hardest tests for humans, things like medical exams. And you can see an example of that here, where we have 4 different models that were asked to or prompted to complete questions on a US medical exam. And you can see the models did great. GPT-4 got 100% of the questions correct, and even the worst performing model still got 75% correct. So this naturally led to a lot of speculation, and we're still seeing the flow-on effects of this, that these models were going to replace doctors, they were going to replace lawyers, and of course, we can't get rid of the claims that they are going to replace developers. But here's the thing. It's been about 2 years since people started making claims like this, and I don't think we're really seeing any material progress towards these fields being credibly replaced. Hasn't stopped managers replacing people, but I don't really trust how robust that replacement has been. So what gives? Well, the problem that we're talking about is that one of the issues with using benchmarks designed to assess something in humans and applying it to LLMs is that we're fundamentally measuring different things. So let's talk first about what these sort of benchmarks are designed to assess in humans. So let's say we've got medical exams. These are meant to be a proxy for how well people will function as doctors. It's pretty simple, right? So in that sense, they do have some validity. Findings have found that people who do very well at entrance exams for med school tend to go on to do well at med school, and then those that do well at med school tend to be good doctors. So we have relatively good validity here. The reason that exams can act as a proxy for future performance in humans is because doing well at a medical school exam and practicing as a doctor both tap into the same raw general ability that humans have. It's called G, or general intelligence. General intelligence allows people to do things like apply learned skills and apply reasoning to the completion of exams and to the practice of medicine alike. So what does it mean when LLMs score really well at assessments like this? Well, it means that they're really good at completing exams like medical exams. Nothing more, nothing less. I know what some of you are thinking. This seems like a very out-of-hand dismissal, right? Can we really be so confident? Well, the difference is how machine learning models learn. So the training of a machine learning model is a very cumbersome process. For something like an LLM, something called supervised learning, what you'll need to do is input a batch of training data. You will then get the model to make predictions over that training data. You will then compare those predictions that the model has made against the real answers, and then the model will internally adjust its weights. So if we're talking about models like LLMs, this would be whether they have correctly predicted the next word. And this is all these models are trained to do. Just the prediction of next word is complex because language is complex. So to build a model that's of sufficient size and complexity to be able to accurately predict next words, they need to be quite large, and they need to take a lot of input data in order to have enough examples. But this is all this model has been optimized to do. And the design of models, because this training process is so cumbersome, especially when you start talking about the scale of things like LLMs, we have built-in mechanisms that force models to optimize for their stated training goal, things like gradient descent. So the chances of this deviating off into something like general intelligence just by chance is extremely low. Now, I can't get into this in too much detail. If you came to my talk yesterday, there's a whole section on intelligence. There are recordings of that talk up from previous times I've given it, so if you want to catch it, send me any questions. If you have outstanding ones, please let me know. But please feel confident that there is very little evidence that LLMs are showing artificial general intelligence. So here we can kind of say benchmarks for humans are not really appropriate for LLMs. So let's take this at face value and move on to assessments that are designed specifically for LLMs. So up until the middle of last year, this pretty humble looking table was one of the key ways of assessing open source LLMs. So this was created by a company called Hugging Face. And what Hugging Face would do is they would take open source LLMs, run them over a bunch of gold standard benchmarks that were designed specifically to assess LLMs, and then they would aggregate the results and then rank them, and then you would get the best open source models. But in around June of last year, this table was retired, and a bunch of new benchmarks were brought in, and a new updated table was created. So what happened? Why did they do this? Well, there were quite a few reasons. Hugging Face has a very interesting blog post about this, actually, which is in my references. By the way, I will be sharing a QR code at the end of this talk, which has all the references I used and all the slides. So if you want to follow up on anything, it will be there. But one of the most hilarious reasons that they retired this these benchmarks was that they were not quite the gold standard that people had held them up as. So let's start with the MMLU. We saw the MMLU actually mentioned a little while ago when I was saying, you see the marketing material for LLMs from these companies, and they talk about how well they performed on this particular benchmark. Now, the MMLU was a favorite, particularly for proprietary LLM providers, and they would be comparing the MMLU scores between their models down to a couple of decimal places. So this must be a pretty phenomenal measure, right? Like, we can measure down to 2 decimal places. It must be pretty accurate, right? Well, people went through the questions on the MMLU, and they found a few things that didn't seem quite right. So I'm going to present you with one of them, and I want to make clear, I haven't trimmed this, I haven't removed any context. This is the full question that the poor LLM has to answer. The complexity of the theory. Okay, so we have an answer key, so maybe the answers will have a little more context. 1, 2, 3, 4, 1, 3, 4, 1, 2, 3, 1, 2, 4. This doesn't match up to anything. The LLM has no more context. It somehow has to work out that the correct answer is C from this. This is not the only question like this either in the MMLU. All right, let's have a look at another benchmark. So we have HelloSwag. This was included on the original Hugging Face leaderboard. Now, HelloSwag became a little bit notorious because around 1/3 of the questions are like the one I'm about to show you. So the idea of HelloSwag is an LLM is presented with a situation, and it has to pick what's most likely going to happen. Okay, so again, all the typos, they're not mine. Men are standing in a large green field playing lacrosse. People is around the field watching the game. Men are holding T-shirts watching into lacrosse playing, are being interviewed in a podium in front of a large group, and a gymnast is holding up a microphone for the announcers. Are running side to side of the field playing lacrosse, trying to score, are in a field running around playing lacrosse. Now, again, poor LLM. But even if this wasn't like a fever dream to try and consider, I think what we're supposed to say is that the men are playing lacrosse. But option C and option D both say this, so which one is correct? By the way, I highly recommend this HelloSwag or HelloBad article. I actually had to pick this one because there were a couple that were worse, but I couldn't read them out without laughing. So if you want a little bit of light entertainment, I recommend that article. Okay, one more. And I actually promise you, I could have filled the rest of the talk with just examples like this. It was C. It was C. At least it wasn't A. Okay, so one more. This is from Common Sense QA. This is another very popular measure. So we can see from the start we're off to a better kind of beginning. The question makes sense. There's no typos. But wait till you see the answer key. Warm air. Continue to live. Going to sleep. Hyperventilation. Stay alive. So, like I said, dozens of such examples were found in the previous gold standard benchmarks. So, Hugging Face retired these measures, and better ones, more robust ones were brought in. So, now we have a new leaderboard. So this leads to the question, does scoring 100% in all of these new measures mean that an LLM is good? Well, we still got half an hour left, so I think you can guess the answer to that. And one of the problems we have is something so fundamental. You're not going to believe it. It's actually in how we ask the question. So there are 2 ways that we can get LLMs to generate an answer for a benchmark question. We can get them, just like with humans, to generate, pick one of a multiple choice list. So if I were to ask what is the capital of Portugal to an LLM and it picks something like B or Lisbon, this would be the correct answer. We can also get it to just generate an answer without having an answer key to reference from. So again, if we ask what is the capital of Portugal with no answer key, and it enters something like Lisbon, or the capital of Portugal is Lisbon, this would be correct. Okay? So far, so familiar. This is how we assess things for humans. And something that you might have noticed on the previous examples is that all of these benchmarks so far are using multiple choice. They provide answer keys. And the reason for this is working with text is hard. And so it's quite difficult to assess whether something that was just generated freely by an LLM without reference to an answer key is actually correct or not. You have to compare it to some sort of gold standard answer, and it's not actually that easy without manual checking to know if they are equivalent semantically. So what's the problem then? Why don't we just use multiple choice answer keys for every single benchmark? Well, the problem is that the type of answer that the LLM is asked for seems to affect their performance on these benchmarks. So what we have here are the answers given, the percent of questions correct by 3 LLMs for 1 benchmark. So this is the percent that the LLM got correct when it was given the option of answering from a multiple choice answer key. And this is the percentage that it got correct when it had to just generate an answer without an answer key to reference from. So not only can you see that each of the models performed worse without the answer key to reference to, it wasn't getting the same questions correct between the 2 answer types. Now, this is a validity issue. These 2 types of answer keys are not measuring the same thing. And researchers believe that having an answer key provided, a multiple choice list to pick from, allows an LLM to rely more on rote memorization or pattern matching, whereas having to actually generate an answer without something to reference to requires a bit more reasoning and kind of taps more into the things we're actually trying to assess. So kind of a big problem here. Another problem, another validity problem we have with measuring LLMs is that these benchmarks don't seem to correspond with performance on things that measure the same sort of concept but are much simpler. So we can see an example of that here. Let's consider this puzzle. Alice has 3 brothers and she also has 6 sisters. How many sisters does Alice's brother have? Now, you're all developers. I know you love solving problems, so I'm going to give you a few seconds, have a think, and shout out the answer. It's no fair, Phil. I know you've seen this talk before. Don't be shy. 7. 7. Well done. So just to walk you through, we know that Alice is a woman's name, and there are another 6 sisters. So we add the 2 together. We get 1 plus 7 sisters for all of Alice's potential brothers. So this is part of a suite of puzzles called Alice in Wonderland. And they're all very similar to this, not really any more difficult. And they're designed to assess very basic reasoning. So what the authors, the creators of the Alice in Wonderland puzzles did is they got a bunch of state-of-the-art LLMs to complete all of these Alice in Wonderland puzzles. And then what they did is they got the LLMs to complete the MMLU. Now, what the MMLU is supposed to assess at its core is reasoning. So what you would expect is that the performance between the MMLU and the Alice in Wonderland puzzles should be highly correlated. It should lie very close to this line. But instead they saw a pattern like this. What's going on here? Well, what you can see, if you look up the y-axis, that the models are getting more than 50% of the MMLU items correct, but they're getting less than 5% a lot of the time of the Alice in Wonderland puzzles correct. Again, I cannot stress how simple the reasoning in Alice in Wonderland is. MMLU reasoning is supposed to be more difficult. So how can these models be performing better on the MMLU than on Alice in Wonderland? So this points to a couple of problems. It seems that the MMLU may not be measuring reasoning in the way that we assumed it was. And worse, maybe it means that the reasoning capabilities of LLMs have been overstated. And the thing is, these are language models. It's in the name. So should we be trying to assess things like reasoning and other such things that are outside of the realm of pure language problems? So The thing with machine learning assessment, and I've kind of been talking about this all throughout the talk, is machine learning models are trained to do specific things. And therefore, the assessment of them tends to be quite targeted when we're talking about traditional machine learning. So say we're talking about an image classifier. Talk about this model that can tell whether a picture is a dog or a cat. That is how you assess it. Give it pictures of dogs and cats, see how many it gets correct. And in the beginning, the assessment for LLMs was pretty targeted. They were initially developed as machine translation models. And so that was what was assessed. And as we realized that these models were more generalist in terms of their language capabilities, we started creating more and more language assessments, things like question answering, things like summarization, things like text classification. But as the capabilities of these models expanded, or appeared to expand, we have created more and more exotic measures for these models. And we now have assessments to see whether these models can do things like advanced reasoning, whether they have deep knowledge about technical areas or things like social sciences, and whether they have artificial general intelligence. Now, this is one of the core validity issues for me. What we now do when we try to assess these models, like on things like the leaderboards, is assess them on so many different things that we're not even sure that we can assess them on, that when you come along as a consumer, you try to pick a model for your use case, how do you know if it's good at doing the thing you need it to? So I've been bashing LLM benchmarks for about 20 minutes. So you might think, is there an alternative? And those of you who are, again, in the weeds of this, might be screaming at me internally. What about the chatbot arena? Those of you who have no idea what I'm talking about, you're probably thinking yet another extremely weirdly named thing. It is true, we love weird names in machine learning. So what the chatbot arena is an experiment, a very large-scale experiment. And it's accessible as a website, anyone can go to it. And what happens when you visit the chatbot arena is you are asked to enter a prompt of your choice. You can see I've chosen, please write me a poem about sausages. Then what the chatbot arena will do is it will go away and randomly pick 2 state-of-the-art LLMs and present the results, their output to your prompt. And you are asked to pick which one you like best. So I'm quite partial to this second poem. Plump and juicy in a row they lie, sausages waiting to satisfy. Now, the chatbot arena basically takes all of these experiments and combines them together in something called an ELO score. And this ELO score is then used to rank and rate LLMs, and they have their own leaderboard as well. So the chatbot arena has been held up as one of the most reliable way of assessing LLMs at the moment. And it is true. It does have high validity in the sense that it's based on more than 1 million experiments from very diverse users who enter very diverse prompts and have diverse opinions. So yes, it is true that it does have validity in that sense. But where it doesn't have validity is in the term it's using to assess the outputs. So you may have noticed that the terms used to assess whether an LLM output is worthwhile is good, better, or bad. What does this mean? How can you compare this between different LLM prompts and outputs? You know, does it mean more funny? Does it mean more concise? Does it mean more correct? More verbose? Does it mean, I don't know, my sausage poem being good? Does it mean the same thing as if you want a eulogy written for your aunt's funeral or a resignation email to your boss? Like, these are not comparable things. And again, trying to stretch these models so far, to try to make their applications so broad, to make them solve everything that might do with language and beyond, people like the creators of the chatbot arena are forced to use a term that is so vague that it's essentially become meaningless. So we've been talking a lot about validity, but we haven't really touched on reliability. So let's circle back to our old friend data leakage. And if you were in my talk yesterday, you would have seen this example before, because it's such a beautiful example of data leakage. So we know all these claims 2 years ago about how GPT-4 was going to take our job as programmers because it was solving LeetCode puzzles and the like. There's a guy called Horace He. He's one of the creators of PyTorch, if you're at all into deep learning, and he started to smell a rat. He's like, I think we've got a data leakage problem on our hands. So what he did is he went away and he got 10 puzzles from a website called Codeforces. And Codeforces is very interesting because the date that each puzzle was released is clearly timestamped. So he got 10 puzzles that were released during the time that the model was being trained. These could conceivably have been in the training data. And then what he did is he got another 10 puzzles of an equivalent level of difficulty that were only released after the model was trained. So in the first instance, the model got every single one of the puzzles correct. And in the second instance, it got every single one of them wrong. This doesn't smell right, right? So another researcher, Sayesh Kapoor, wanted to confirm that, in fact, the reason that the model did better at the first set of puzzles is because it had explicitly trained on them. So what he did is he asked GPT-4 to tell him about a puzzle that was available at the time it was trained, and the model obligingly vomited up the source. It had, in fact, been trained on Codeforces puzzles, and that is why it was getting this exceptional performance. The problems with data leakage go deep, and they are an absolute scourge when it comes to assessing LLMs. So another team of researchers, they went through and they did a review to see how many benchmarks, the benchmarks themselves, had leaked, at least partially, into the ChatGPT models. And they found that over 100 of these benchmarks had at least partially leaked into the model, which means these models have an inflated sense of performance on these benchmarks because they've already seen some of the answers. And you can see that this affects all the major ways that we assess LLMs. Natural language capabilities, math, programming, translation. The thing with leakage is it is a problem that if we continue scaling models, which we may not do after DeepSeek, obviously the direction is changing, but with the hyperscaled models, their need for data is so huge that it's going to start outstripping the amount of usable text data in just a few years. So the way that this scaling of models has gone is that over the past 4 or 5 years, the way to reliably increase performance in models is just to make them bigger and feed them in more data. Like I said, January changed everything because DeepSeek can actually get good performance with a smaller model architecture and less data, but scaling has its concerns, and one of those concerns is data leakage. So we went from GPT-3 in 2020, which was trained on, how much? 500 billion tokens, all the way up to Llama 3 last year, which was trained on 15 trillion tokens, a 30 times increase in the amount of data in just 4 years. The problem is that the amount of usable text data is thought to top out at around 300 trillion tokens. So if we keep pursuing a path of scaling data, we're going to run out of usable data in just a few years. So this creates a data leakage problem like we've never seen before in machine learning. What it means is that the things that we have available to actually test these models will all have been consumed by the models during training. There will be no more fresh data left. So the way that this is being worked on with the newer generation of benchmarks is that they're being kept completely private. So they're not available within the training sets of these models. But it's something to really think about as a lay user. If you as a lay user is using one of these hyper huge models, there is a good chance that anything you're passing in to just informally test it is something the model's seen before, and you can't trust its performance. So finally, I want to talk about one of everyone's favorite topics when it comes to LLMs, which is prompt engineering. We all love that. But I'm going to be talking about something quite concerning and quite depressing when it comes to prompt engineering, and that's something called prompt sensitivity. So LLMs are incredibly sensitive to how you phrase their prompts. I think anyone knows that as a lay user of them. But you may not be aware how sensitive they are. So let's say we want to do a text classification problem. We have a passage of text, we have a potential list of categories that we want to classify it into. So maybe we can create a template and pass in the passage and the categories in this sort of format. Or maybe what we can do is do it in any of these formats. So can anyone spot the difference between these? Just shout it out, don't be shy. There's no tricks. Yeah? Perfect, perfect. So, yep. Spaces, new lines, punctuation, capitalization. Very minor differences, right? These are all semantically equivalent, absolutely identical. So these changes in the template format shouldn't make a difference at all, right? Right? Wrong. So this line here is the performance of the model in the classification task. We go from 0, got everything wrong, to 1, it got everything correct. And these insignificant differences led to a total of 77% difference between the best and worst performing prompt. Now, as someone who has worked in data science for 9 years, I cannot tell you how bad this is. If I were to create a machine learning model that sometimes got almost everything wrong and sometimes got about 80% of things right, I'd be fired. But this unfortunately is very much part of the fabric of LLMs. Just to show you this is not a one-off. Here we have a group of models that were state-of-the-art probably about 1.5 years ago, maybe a little bit sooner than that. And again, the same sort of experiment was repeated. These models were fed different but semantically equivalent prompts. And what we saw for each of them was a 30 to 50% difference in the performance. Now, this is compounded by the fact that there is no universal template when it comes to working across all LLMs. You can't just basically create one template to test all LLMs and compare them. And what this means is the results you're seeing from the creators of LLMs, from the researchers and from the companies that create them, these are going to be the best possible result that that model is going to get. What it means for you as a developer using the LLM, you may not be able to get anything close to the performance of that model compared to what's being reported. So I spent this whole talk telling you about all the problems with LLMs. I actually remember, Phil, you telling me how depressed you were at this point in the talk last time. But there is a silver lining. So maybe you're thinking, what's the point of using LLMs? I can't trust them. How do I actually know if I've got a good model? And I have a solution for you, but it's not as sexy as benchmarks, and it's not as easy as leaderboards. It actually has a lot in common with the way that we've been building and assessing software and machine learning models for decades now. So a machine learning engineer called Hamel Hussein wrote this incredible blog post. Again, your AI product needs evals. It will be in my reference list, which you can get in the QR code. This is an exceptional blog post, and I would recommend anyone who is an engineer having to work with LLMs read it, because it is very, very insightful. So he tells the story of how he works at an AI consultancy. And he was brought in on a project to try to build an AI chatbot interface to help real estate agents find information. So initially what he and his team did is they just picked a model that was good from the leaderboards, and they created a prompt template to try and cover the basic use cases. But very quickly, the model started coming into use cases that weren't covered in the basic prompt. So they started expanding the template, and it became very, very complicated. And the only way they really had of assessing it was vibes. Like, it just seems better. And he's like, this is no good. We need to take a step back. So what they did is they started from the beginning. And what they did is they built in, firstly, unit tests. Then what they started doing was logging traces. Now, this probably feels much more familiar. It feels much more like software engineering and less like LLM magic. And then, once those foundations were in, they started introducing higher levels of evaluation, things like manual evaluation and A/B tests. And this allowed them to start experimenting. changing around their prompts in a controlled way, introducing new models, and building it all into this virtuous cycle that allowed them to iterate quickly. So let's just briefly go through the different levels of assessment that Hussein talks about in his blog post. So the first are unit tests. And you can use unit tests in much the same way you would when you're building a traditional software system. The one thing to understand is because you're dealing with a non-deterministic system, sometimes your unit tests are just going to fail. And you need to work out internally what proportion is an acceptable fail rate. A little bit like doing statistics, actually. So let's say we want to assess a very specific function. Let's say the real estate agent asks for Emily Johnson's phone number. So what the LLM is going to do is to generate a query to the CRM. What we would expect to be returned is a phone number. This is an array that contains one piece of information. Easy, right? If we know the format that the phone number is meant to be in, we could even write a finer-grained unit test. But this is all fundamentals that we all know. And we can also use LLMs to generate unit tests for us, not to write the unit test, but to generate fake contact details and the potential query that the user might use. And again, I want to stress, you are doing engineering, so you need to think, what are sensible unit tests to write? Don't outsource that thinking to the LLM, but you can, of course, get them to help with the code and just go through and check it yourself. Now, this sort of approach has very high validity because we are just assessing one thing concretely defined. Now, we move on to the next level, and this is where Hussein recommends getting humans involved in the loop. Again, this will feel familiar to many of you. So let's say you want to have a look at your traces. The traces in the context of this system are the multi-part interactions that the LLM has with other parts of your system and your end user. So what you want to do is get someone to go through and start manually evaluating that, checking whether it's good or bad. And this is going to be a lot of work, right? But you don't need to do it for everyone forever. You just need to get a good representative sample of the type of interactions your users are having with your system and your LLMs are having with the rest of the system. Once you have this data set, what you can do is start automating. So you get another LLM, hopefully one that is a bit more powerful than the one you're using for your system. And what you try to do is get it to start converging on the answers that your human raters have given you. Now, this is going to have high reliability because we have two ways of assessing the same thing, and the gold standard in this case would hopefully be your human evaluators. And then finally, A/B test. This works pretty much the same way it does with any system. In this case, we would mess around with things like different prompts, different models. Maybe you want to have a smaller model, maybe a bigger model, maybe a more specialized model, or maybe you want to start fine-tuning your own model on domain data. And of course, this is going to have high validity because you're testing directly on your end users. You're seeing how that system works in production. And potentially, you can also use this to maybe tune the fit between the prompt and your system. And maybe that's going to lead to higher reliability. But from what we've seen about prompt sensitivity, it's a bit unpredictable. So that brings us to the end of the talk. So we took a deep dive into how LLMs have turned traditional machine learning assessment on their head. And in trying to take shortcuts, in trying to create measures that cover every possible use case we've dreamed up for these models, we've really just gotten ourselves confused. And we have furthered the gap between assessment and reality, and we've built up a lot of the myths around this model that, again, I talked about yesterday in my talk. What we need to do is go back to our fundamentals, our machine learning fundamentals in terms of measurement, and our software engineering fundamentals in terms of monitoring. We need to go back to building robust, reliable, and valid measures that are specific to our use case. So here's the promised QR code. Here are my socials. Thank you very much, and thank you for being at the conference. It was really nice to see you all. I think we have about 8 minutes, 7 minutes, if there's any questions, or go ahead.
So, the really like first semester machine learning, you know,
yes,
cross-validation,
yes.
you know, overfed problem. Like, how is nobody talking about that?
I will not try and take credit and say I'm the only one talking about it, obviously. If you go through this reference list, you'll see a lot of wonderful pieces about this. The problem, am I going to say something's bold on recording? Yeah, go ahead. The term AI is not a good term. The term AI is a marketing term at this point. What we are fundamentally dealing with is machine learning. And the more that we talk about this as AI, the more we confuse the issue. Even the fact that it seems surprising to people that DeepSeek, and even Falcon before it, Falcon was about a year and a half before DeepSeek, these are models where people are like, what if we try curating the data and putting in higher quality data? Wow, like crazy. Who could have thought of such a thing? It's not that simple. Cleaning data at that sort of scale is really difficult, right? But these seem to be surprising things to people who are consuming these models. So I think it's marketing. I think that's what happened. And we want to desperately believe that we're not dealing with natural language processing machine learning models. We're dealing with AGI. That's more the side that the thinking has gone on. And hot prediction this year, hype bubble's going to burst. I said it last year, so I was wrong, but I want to believe. This is what I want to believe. Another question?
I mean, we know code is very well structured as opposed to like natural language.
Mm-hmm.
I believe that in code they are going to perform much better, and there is going to be a lot more like data to train on. Start like giving access to public or private repositories. Yeah, I mean, what are your thoughts about how it could perform better there than?
Because it's a specific domain. Yeah, this is something I've been saying from the beginning. Look, obviously, a bit of bias, right? Like, we've got our own products at JetBrains around AI code completion. We actually just released an open source code completion model, Melon. Have a look on Hugging Face, it's very cool. But because you are dealing with a more specific domain, and the really kind of important thing with constructing training sets for code is there's a lot of bad code, mediocre code. There's a lot of code written by people who are learning in public repositories. The real trick is making sure you curate it so you have the higher quality code firstly in the training sets. But the really nice thing about coding as a use case is you have two methods of validation. You have an expert who should be checking. Please do not commit code that you have not written yourself, at least in some degree. But we also have compilers or interpreters who can throw errors, which can throw errors. They're not people either. So yeah, I do actually see it as a more promising use case. And it's partially because it is so focused with multiple checks and balances, more objective. One more question, I think. Yo.
To add to that, the first comment that in the specialized field like in security, you see this quite a lot. And when you don't really know what code being generated for you, and it's a lot of big issues. And it's kind of convincing for people that this is a secure code, but in reality it's far from it. And a lot of these things we know is being trained on Stack Overflow answers, which back in the days we were actually poking a lot of Stack Overflow answers because they were full of security vulnerabilities, and now they're in the system. So you actually see this limitation, but that's just come back to it because of all the marketing and hypes around it.
And just to sort of summarize, so we're talking about like the problems with security because the code might be outdated or not from a high quality source. Firstly, I want to congratulate all security engineers on your job security in the coming 10 years. I am sorry about the messes you will need to clean up. But kind of a couple of points on that. If you're using models just with the parametric knowledge, that is the knowledge that is contained, that it learned from its training set, you have these particular problems with outdated information. Like that's where it's particularly vulnerable. And if you're ever going to use LLMs to give you information about something that needs to be cutting edge, like security, you should be using it as part of something like a RAG system. Like it should be pulling in the latest information from, say, a web search or a database and giving you that. But yeah, it's a really good point. And I think we all saw that example of a guy who was bragging on Twitter, I think, about how he's like, we don't need developers anymore. I just built my own application, and I don't even know how to code. And then the next tweet was, I'm getting attacked. Someone's doing a DDoS on me, and like my database got hacked. And it's like, yeah, it's not just code, man. It's all right. I think we're out of time. I'm going to be around for probably, what do you reckon? 5 minutes. I'll be going to get beers at some point. Yeah. Beer deluxe. We're going to go for beers because we are Australian, and we can talk about AI. And we're free! Yeah! Thank you!